let's just say that the induction hypothesis goes like this, okay? For some k, okay, where k is an integer, okay, and it's between 2 to the n, so k is more than or equal to 2 but less than n, okay, k has a unique, I can't spell it, unique factorization. Okay, so this is our induction hypothesis, something that we assume to be true, but okay, we don't know yet, but let's just assume it to be true to prove the main proposition like that. So k has a unique factorization, right? Okay, now let's just say, suppose that n, okay, has two distinct factorizations. Okay, we don't know, but let's just assume, or let's just suppose that it has two distinct factorizations. Okay, so what I can do is that I can let n equals to p1 E1, P2, E2, all the way to PS, ES, which is equals to, okay, Q1, C1, Q2, C2, all the way to QT, CT. Okay, quite a big statement like that. Okay, so now we are going to show that it has two distinct factorizations. Now, obviously, that doesn't fall in line with our main proposition. But what I can say is that hopefully through the reasoning or through the deduction, there's a contradiction somewhere, and you know the unique factorization thing would come up like so. Okay, now if n is prime, now we're going to split the case up again into n is prime, n is not prime. So if n is prime, okay, what do we have? We have n is equals to p1, which is the prime number itself, and which is also equals to q1, which also is another prime number. So this one is, the factorization is unique. Why? Because this has to be equal to this. It's a prime number, it can only divide by itself. So we will just say that proposition is true. Okay, so that is the easy part. Now for the difficult part, which is a bit difficult to motivate. Okay, if n is not prime. Okay, now n is not prime and n has this factorization like this and like this. Okay, let's just focus on this one over here. Okay, now if n is not prime, I can write p1, okay, divides n. Now what does this statement mean? It just means that I can take n divided by p1 and I get no remainder. Okay, so but I is read as p1 divided by n. P1 can divide by n, okay, and then that would give us, okay, n divided by p1 is equals to, simply take this one and reduce the power by 1. Okay, e1 take away 1, then followed by p2 to the power of e1 minus 1, e2 all the way to ps, es. Okay, so that is just what I'm saying. P1 can divide n. However, okay, remember that we have stated n to have two distinct factorizations like so, right? So now what I'm going to write is that I can say that since p1 divides n, p1 also divides n, okay, where now I will use the second expression, which is q1, c1, q2, c2, all the way to qt, ct. Okay, so I hope we can get this. Okay, now n is equals to this two over here, so p1 divides n, which is this one over here. That will also mean that p1 will divide the other expression, right? The other distinct expression that we kind of, you know, suppose in the beginning. Okay, so if this is the case, okay, let's just focus on this thing over here, which is going to be a bit difficult to explain, but I will do my best. Okay, p1 can divide this expression over here, knowing that q1, q2, and qt are all primes. Okay, distinct primes at that. Okay, they are distinct primes in their own expression. These two are distinct, but this one is also distinct primes, because if their primes are the same, we just multiply them and raise the power. So q1, q2, qt are distinct primes, and p1 is just a prime number. So if this one divides that, okay, does it make sense that I can write for some I, p1 divides qi, okay, ci. Okay, so this statement means that somewhere hidden inside there, okay, there's a prime number raised to a certain power ci that p1 can divide that. Okay, now you may take some time to think about it. Okay, let's just take some time to think about it. You might be deceived in thinking, or at least if you are skeptical, okay, that down here, there is no prime that I can, how to say, there's no prime number over here that's equals to P1, okay? Meaning that P1 cannot divide a single Q1 or Qi, which I've written over here. Now, if you're thinking along those lines, I will just write another statement for you, okay? Sorry, yeah, n is equals to x and y. Okay, let's just look at this small little case over here. N is equals to x and y, right? That means we can factor n. So, and you also know that x and y are primes, are distinct primes, okay? So if I can take a prime number, okay, and I can divide it by n, okay, wouldn't that mean that I can also take that prime number and divide it by x, or I can take that prime number and divide it by y? Does it kind of make sense over here? Now, P, we start off as a prime number, right? Which is over here. Now, P1 is a prime number. Now, n is not necessarily a prime number, okay, because n is not prime, but we can re-express it as a prime number over here. So, the property of a prime number, okay, is that you can't further express it down. It's already in its, how to say, in its sole form, or its purest form, because prime number, that's what it is. You can divide it by itself or 1. So when we reduce, okay, n into like components or factors of prime numbers, which is its purest form, okay, that would mean that whatever prime number that I take over here, which can divide by n, that prime number is either going to divide x or it's going to divide y, because I already have reduced it in its purest form. Okay, now I'm not going to spend too much time on that. Okay, there's actually a corollary on this, okay, which I did not state formally, but this is just a short example to illustrate it. Okay, if the prime number divides n, okay, which I've shown over here, this P1 divides n, okay, that would imply that the P1 would divide over here, and hidden inside there, just like hidden inside this n over here are prime numbers, the prime number would have to divide one of them, okay, because like I said, it is in its purest form. Prime number, okay, very interesting property. So we can write this over here like this, okay. For some I, P1 divides Qi. For P1, P1 divides Qi Ci. So upon rearranging, we can just simply write P1 divides Q1 to the certain power of Ci. Okay, I will just simply find that hidden prime number inside there and put it inside, and yeah, put it inside here like this. Okay. Like that. So what does it mean? That means P1 has to equals to Q1. Okay? I hope that makes sense. P1 divides that, this raised to a certain power, so P1 has to be equals to Q1 because they are both prime numbers. Okay? So the final step, if you have been following with me, so P1 divides this, now we can write upon rearranging, okay, we will just take it from here and divide by P1 is equals to P1. Okay, so I'm dividing it, I raise the power by 1, P2, E2, okay, PS, ES, now equals 2. Let's focus on the second one, which is the second one over here. Okay, remember, Q1, I re-expressed it, right? Q1, I re-expressed it as P1 from this statement over here. So P1 is equals to Q1. I've rearranged it, put it at the front, so now that would give us Q1, C1, take away 1, Q2, C2, Q, all the way to QT, CT. Okay, I hope that makes sense. Yeah. Okay. So now, why do I want to do that? Okay. So now I just showed you that for some n, right, that has two distinct factorizations. Okay, we're almost there. Just hang with me. N has two distinct factorizations over here, right? Okay. But I've just shown it to you that both can be divided by P1. Okay, over here like this, because P1 can divide n, okay, and so P1 can divide the right hand side, okay. So now the final statement that I'm going to write is that, okay, 2 is going to be less than or equals to n divided by P1, okay, but this, you see, we know that this would have to be less than n like so, okay. Now that's the final statement, okay, and it just follows suit. Why does it follow suit? Because, okay, we have used the induction hypothesis over here, okay, that for k which is more than or equals to 2 but less than n is the unifactorization. We have proven that the induction hypothesis is true for k is equals to 2, okay, therefore this one fits over here, and whatever value that we pick, okay, that would be more than this or would be more than 2, okay, we can just simply reduce it to the one over here, okay, and then that would give us that it would have a unique factorization. Okay, let's just put in some numbers. So n is equals to 3, 3 is prime, so 3 is prime, check. okay, n is equals to 4. You see, n is equals to 4, I can now divide it by 2, okay? I can divide it by a prime number over here, and I know that this thing has the unique factorization from the induction hypothesis. So on 5 is prime, then I go to 6, I can now express it again as this, okay? And then this would have the unique factorization, and so that's why 6 would have the unique factorization, okay? This, I would say again, is the induction process. And lastly, if this have a unique factorization, I will just simply go back to the step over here like this, and I'll write for this one over here, okay, P1 is equals to Q1 and E1 is equals to C1 here. Just formally stating the unique property.